Hello, my name is Keh-Harng Feng. I'm the current captain for Team Darwin Spark and also the project lead for our application. We call it InCite. And the team consists of essentially, well, two members, myself and Dazo, who was responsible for the graphics and user experience of the application. But I feel like I should give an honorary mention to our former team member, Bryan Glogowski, who was responsible for the data. Okay. So here's some motivation for the application. Right now we're essentially living in the information age, and here's a little picture that I stole from Nature. What it shows is that the global scientific output basically doubles every 9 years. So here's a little scenario. Let's say I want to learn about computer networks. Here I have two papers. First one is called Ethernet Distributed Packet Switching for Local Computer Networks. The second one is called Router, a methodology for the typical unification of access points and redundancy. Question is, which one should I read first? Now, the first paper, Ethernet, is actually written by this guy, Robert Mech, back in the 70s. He was the creator of the Ethernet architecture. So if you want to learn about computer networks, well, this is a good place to start. The second one, Router, is actually a fake paper generated by this program called SciGen. This was created by 3 MIT computer science students. They submitted this paper to a real conference, and surprisingly, it was actually accepted. So this caused a lot of controversy. People talking about, the validity of this conference, but also how do we tell a fake paper from a real one? So what I think this really highlights is the fact that not all things are created equal. We want to present to our users a tool to help them find the best resources that they have. Right, so here's a more clear outline of our goals. We want to facilitate effective searching of articles, scientific articles, and we want to present the quality of articles and associated authors to our users in an easy to understand manner. And third, we're going to visualize the flow of knowledge to allow users to explore associated articles. And finally, we want to recommend similar articles to our users based on their expressed interests. Some of these might sound kind of weird and abstract, but you will see soon what we mean by that. Alright, so here's a little recap on the data. Our data is obtained from the Elsevier Scopus database. Unfortunately, Scopus has a pretty strict API limits for various things, so we made a compromise on the kind of data we have in our database. So we only have articles from computer science, and also for each article we only have a subset of each one's article citations. So what this means is that while everything looks real, they're not. So you should treat them with a grain of salt and really look at things as though it's a demonstration, because that's what it is, instead of like an actual representation of the real stuff out there. Alright, so here is the homepage of our web application. You can see that it's currently listing all of the articles that we have, which is over 1 million of them. There's also many authors, institutes, and citations, etc. And this is how you get to do more interesting things. By clicking on this button, I can now list all of the articles in the database, and there are like 68,000 pages of them, so this is not a very efficient way of doing it. If you want to find a particular article, you should use the search function, and we allow you to subset articles based on, say, the user's first name. Let's say Steven, and this should give you all of the articles subsetted to just authors with the first name Steven. Yeah, you can see there's still quite a few of them, 121 pages of them. You can also do the same thing with their last name. You can do them both. For example, Stephen Robinson, and this should find the articles written by someone with first name Stephen, last name Robinson. And if there are both of them, if there are multiple Stephen Robinsons, you will find articles by all of them. Alright, so the more interesting search function is search by title. And you can search by title using terms, keywords, or phrases. I'm going to explain a little bit about why our search is not a simple word matching from the title string. So first I'm going to talk about the properties it satisfies. Alright, so for an effective search to happen, you should essentially satisfy the following properties. First, you want to match words that are similar to what the user typed, not necessarily identical. So for example, the word compute and computation should probably be matched to the same thing, right? Because they have very similar meaning. Same thing with optimize and optimizing. So essentially you want to standardize the search strings or the search words. Also, you want to display your search results to the user in a sorted manner. So you don't want to just simply label some of the documents as relevant and some of them as irrelevant. What you really want to do is you want to give all of the documents a score based on what a user searched for. And why do you want to do this? Well, for one thing, if you just match them, if you just label them as relevant and irrelevant, then there's no way to tell which relevant document you should serve to the user first, right? But if you have a score, it's very easy to do. You just serve the highest score to the user first, and then sort them by their search score. And then we want to penalize and ignore words that are really useless. For example, like the, like like I. Like these are words that are not useful, so you can pretty much just ignore them. This is called stop word removal. And finally, you should adjust each word's weight based on the document length and the overall document frequency of this word in the corpus. So what do I mean by this? Well, first imagine that you have two documents, one with a very short title, one with a very long title, and they both contain the words that the user searched for. Okay, the short title document, well, clearly the relevant words have a much higher proportion compared to the entire title. So you can consider the first document as being the shorter document as being more targeted towards what the user wants. The longer one, I mean, sure, it might be relevant, but just because of the fact that the title is so long that it has a higher chance of containing those words in the first place. So you can think of it as being someone who's talking too much, right? So like he might have mentioned what you want to hear once or twice, but overall it's not as relevant as the first guy who immediately got to the point and told you exactly what you want to hear, right? Okay, so about document frequency, right? This basically accounts for how frequently this word appears in the corpus. So why is this important? Well, think about it. Like right now you have a collection of documents. In our case, all the documents are from computer science articles. And let's say somebody tries to search for a term, a compound phrase, like for example, quantum computing, right? So computing is a very common word in articles from computer science. You can imagine almost every single article might have the word computing at one point appearing somewhere, right? The word quantum, on the other hand, is very specific, right? So basically, only people who are doing quantum computing or cryptography will mention something like that. So if you're searching for the term quantum computing, quantum, the rare word in the collection, it should be considered to be more relevant compared to computing, which is very common, right? So it doesn't have that much information. And this is why we should consider the appearance, the overall frequency of the appearance of each term compared to all the documents in the corpus. So let's do a demonstration to show that our search function in fact satisfies all four desired properties that I have listed here. Let's try quantum computing because I mentioned it, right? Quantum computing. Click on search. It's gonna take a while. Here we go. Okay, so you can see that the article listed on the top has the word computation, which is an inflected form of compute, right? Or computing. And also the word quantum. And that's the reason why it's ranked at the very top. Okay. Second one probably ranked similarly to the first one, but it looks like they probably had the same rank score, to be honest, right? Yeah, so this article has the word quantum appear twice. That's probably why it's ranked so high. But you might be wondering, didn't you say quantum is a high information content word that is more important than computing? Why isn't this ranked higher than, say, this one? So I forgot to mention on the previous slide, but we also discourage repetition of words. So repetition matters. Like if you have, say, 3 keywords appearing in a title, it's going to be better than the same thing essentially, but with only 2 of those keywords. Okay, but it's also weighted less for each repetition. So if you have 2 of the same, so if the same keyword is matched twice, compared to say 2 different keywords being matched, right? Then the article with 2 different keywords matched is going to be ranked higher. And that's because like you want to discourage spam, right? So somebody you could be typing something like money, money, money in the email, well, it's still spam. So you don't want to place too much weight on something like that. And that is the reason why this is not ranked as high as, say, quantum computing. So similarly for this one, it has the word quantum, but no computing, right? And in fact, you don't see the word computing until you get to here, where the word computer appeared, right? Which is probably normalized into the same thing as like computing, computation, etc. And the computer, this word appeared twice in this article. That's the reason why it's ranked so high. Then you have this computation of compressible multifluids. Computation appeared once. So you might be like, hey, how come this is ranked higher than this guy, which has the word quantum in it? But no computing. Didn't you say quantum is a more important word compared to computation? Well, the reason is this article has a very long length, so it has a high word count, and therefore it is discouraged, right? And to demonstrate that we in fact do ignore words that are not heavy in information, I'm just gonna say something like quantum, well, the quantum computing is awesome. Awesome might not be considered irrelevant, but is and the should be, right? And you can see that the search result didn't really change. And I guess there are no articles named awesome, right? So this small demonstration should show you that our search in fact satisfies all 4 desired properties. And if you want to know why it satisfies those desired properties, I will talk about the implementation later in our advanced functions section. Okay, so we know that our search function works and satisfied all of the desired properties that I have listed. Now we want to present the quality of the articles and associated authors to the user in an easier to understand manner, and also to visualize the flow of knowledge, right? And to allow the user to explore associated articles. So this can be sort of considered as our second advanced functions. Let me search for something that could be, let's say, optimization techniques. Just because, I mean, I've never done this search before, I have no idea what it's going to return. Okay, optimization techniques for system reliability with redundancy. A review. Let's click on this. Let me full screen this. Okay, so here you see that the article detail page, normal stuff like the authors associated with these articles are listed here. You can actually click on them. I'll show you what happens if you click on the authors later. The ISSN, full title, the journal it was published in, the published date, the citation impact. So this number represents how many times the article has been cited by other articles in the database. And you can see what I call a citation impact graph or citation network graph. So what this shows you, let me zoom in a little bit, is essentially articles that are associated with the current article, which is colored in blue. So all of the red nodes, right? They are referenced articles relative to the current nodes. So what do I mean by that? The first level nodes, like for example these two, they don't have anything in between them. They're directly pointing to the current article. Means that they're referenced by the current article, and you can see their citation impact on the nodes. And you can also mouse over to see their titles. And for this guy here, well, that's the first level red node, so it's referenced by the current article. This guy is a second level red node, so it means that he's referenced by this guy, but he's not directly referenced by him, because if he is, then there would be actually an arrow pointing to that. So you can sort of think of the arrows as like a flow of knowledge. So this article is using knowledge as flowing from these red nodes, directly or indirectly. The green nodes are what I call referencing articles, so relative to the current article. So what I mean by that is this guy, for example, he is referencing this article, so the current article exists inside the reference of this guy, and that's why the flow of knowledge is pointing from the current article to the referencing article. And you can also see second level nodes that are referencing the first level referencing nodes, right? And you can see that they have pretty low citation impact, probably because they're published late, not necessarily to their own fault, right? And similarly to here, you can also see that. So right now the graph is generated with essentially a limit of 3 nodes on each level, and the nodes are sorted with the highest citation impact on top, which means that these 3 nodes, for example, are the articles with the highest citation impact that's referencing the current article, and these 3 nodes are the articles with the highest citation impact that is referenced by the current article. And if the user wants to explore these articles in detail, they can click on this. Whoa, look at that. And he will end up going to the detail page of that particular article, which will also show you their own citation network graph, and you can sort of like follow the trail, so to speak, to get to like all the articles that are associated with a particular with the original article. And here I'm going to click on the author to show you the author detail page. So you can see the affiliation of these authors. So it happens there's only one, which means that he has only been associated with Kansas State University for his entire life, at least in the database, right? And you can also see all of the articles that he has published. So he has published 21 articles in the database, and out of these 21 articles, his total citation is 482, so he's been cited 482 times from all of the articles he has. And here's the average citations that he has received. The publishing date, so basically all the articles here are sorted by their publishing date, so you can see his most recent article near the top and his oldest articles at the bottom. Yep. And this is essentially how we present to the user a mechanism for him to explore all the associated articles of the article that he's looking at right now, and also to gauge how important this article is by looking at the citation impact metrics. And by looking at the author page, he should be able to figure out if this author is someone who has published influential papers, or someone who has no citations whatsoever but lots of publications, so probably a fluke, right? Or someone who is trying to game the system. So of course, like the nodes here, you can imagine that they don't necessarily have to be completely separate. For example, this one, right? Like this node is referenced by him, and both of them are referenced by him. So you can foresee that there are cases where one node could be referenced or referenced by common nodes shared by other nodes. So this kind of gives you an idea on which paper is very important. Like for example, this one, since the flow of knowledge, like he's citing all three of these guys, and this is also cited by two of them. This paper is probably something that you should pay attention to. If you're reading this paper and you figure that you want to get a better sense on where this knowledge came from, and what's the next paper to read, then maybe this guy is a good choice. So I'm going to demonstrate recommendation mode, or our third advanced feature, or rather I'd rather call it advanced feature 2.5, because you will see that it builds on top of the groundwork that we have laid out. Alright, so to use the recommendation mode, you have to register a user account on the website. So I'm going to say test user, first name is testfn, last name is testln, email is test. We probably should be using HTTPS, but as a demonstration project, I think this is good enough. Domain.com. Password, I'm just gonna call it test123. Sorry, test123. Password test123 pw. Okay. What? Did I mess up on the email? Maybe it's the it's a space at the end. Well, it's anal about that. Okay, so now I've registered. You can see I'm logged in as test user. Here's a page called My Interest. Except I have no interest right now. We can go to the article list to see all the articles we have. Well, let's do a search. Like I'm from a physics background, so I like physics. This is physics. I don't know, something else cool. Maybe optimization again, network. I don't know. We'll see what happens. Let's say this is the things I'm interested in. Oh, cool. There's an article about physics. Okay. Notice that there is a button called Add to Interest. Let me click on that. Now the article has been added to my interest, whatever that means. Something about physics again. Let's find something else. Fuzzy neural network. That sounds cool. Wow, look at that. And I'll add it to my interest. Let's see if we can find something on the second page. Oh wait, there's an article talking about citation. Okay, well, let's check it out. Put it to my interest. And a bunch of stuff about neural networks. Large-scale linearly constrained optimization. Add to my interest. Right? Okay, so I've added a bunch of articles to my interest, meaning that I've said to the system that these are the articles I'm interested in, and now my interests are populated with the articles I was interested in. So what does this do? Well, notice that we can now select some of them, or all of them. Let's say I'm particularly interested in optimization today, so I want to see other things that are similar to this paper. I can select it. Click on I'm feeling lucky. So those of you who have used Google before, I'm feeling lucky is the recommendation mode for Google, right? And look at that, it has found other articles, excluding the one that was in my interest that was selected, right? That are similar to it based on our query search mechanism, right? Our title search mechanism. And these papers are essentially searched using the interested article's title as my query, which allow me to find other articles that are considered to be similar to it because our search mechanism is quite robust. And this is again sorted using the relevance ranking. So further up on the list, are more likely to be of interest or of similar nature to the selected interest. And you don't have to select just one, right? You can select multiple ones. Like, let's say I'm really interested in physics, so I selected both of them. Articles on physics. And let's see what it finds for us. Okay, something about Monte Carlo, because one of the papers is talking about Monte Carlo. Here again, right? Physics, Monte Carlo, etc. Right? So these are essentially similar to both of these in some way, one way or another, right? And you don't have to select articles of a similar nature, right? You can also select fuzzy neural networks, right? And then you should push out things that are, related to neural networks somehow, somewhere in the recommendation list. We talked about optimization because selected, neural networks, right? So so you can see that by utilizing this, the user can express his interest and get other similar papers that he wants. And if he no longer finds one of the papers interesting, you can always just delete it, and there's only one left. If it doesn't select anything, just click on it straight out. You will use all of the interests that the user has. Alright, so here's a recap on what we set out to do. So we have effectively accomplished the first goal by implementing a advanced search function using natural language processing. We accomplished the second and the third point by basically implementing the article detail page and an author detail page with citation impact metrics displayed there to allow the users to gauge how important a particular article or author is. We also visualize how the article came to be using a citation network graph, so the author can use it to retrace the steps the authors took to get to where they were. And finally, we implemented a recommendation system using our robust search mechanism to allow the users to express their own interests and effectively search for articles similar to their interests. Alright, so that's basically the end of our demonstration of our application functionality. There's going to be a second part of the video that will talk about the technical background behind the implementations and the advanced techniques that we employed to make the application.